Welcome to the course Introduction to Probability Theory and Statistics. In this course, we are going to discuss about the probability theory in 8 modules, followed by statistical methods in 4 modules. It is a very important course in applications of engineering field. Before that, let me brief what is the connection between probability and statistics. Probability and statistics are more related. In this course, we are going to discuss only the introduction to the statistical inference. The connection between probability and statistics is because the characteristic of the population under study are assumed to be known in probability problems, whereas in statistics the main concern is to learn these characteristics based on the characteristics of sample drawn from the population. In a nutshell, the statistics is more of related of the statistics is more of a study with the data, whereas the probability is more of a statistic probability concepts. Whenever we solve the real world problems, we assume some concepts using a probability, but when we want to solve the problem with the more in detail, we take the empirical data and we study the data, then we apply the some of the statistical inference concepts into the data part to make the real world problem in an easy way to understand. There is a one more concept also related along with the probability and statistics, that is stochastic process. That is a separate course, Introduction to Probability Theory and Stochastic Process, whereas this course is Introduction to Probability Theory and Statistics, in which we cover first 8 modules of the probability theory and then 4 modules of the statistics. Even though the statistics is a very big concept, we cannot able to cover in 4 lectures. So, in this course we made it a very introductory level of statistical concepts or statistical methods we covered. We did not go in depth of statistical inference, because each topic which we covered, there are 4 topics we have covered here, and each topic can have a separate course, whereas we have made a very introductory level of statistics in 4 modules. So, we started this course with the probability theory, as a first topic is basics of probability. Then the second topic we introduce random variable. Even though in the school +2 you would have studied some probability concepts and random variable, but we have started these topics again. In the sense we have introduced the probability space, and there are some more probability concepts we introduce. Therefore, any real world problem can be solved without any assumptions of sample space is finite or probability of any sample is going to be equilikely and so on. So, you do not need any assumptions. So, we introduce a Kolmogorov axiomatic definition of probability, so that any real world problems can be solved without any assumptions. So, that we introduce in the basics of probability, and the same concept we introduce in the random variable, like we introduce a little bit of measurable function also, by keeping the probability space is by keeping the probability space we introduce a random variable, therefore, the real world problem can be solved without any assumptions. And in the third topic we introduce moments and inequalities, and yes, in the fourth topic we introduce all the standard distributions. For example, binomial, Poisson, normal distribution, exponential distributions. So, all those both the discrete and continuous type standard distributions are discussed in the fourth topic. And fifth topic we introduce a multidimensional random variable, starting with the 2-dimensional, then 3 and so on. And in the sixth topic we introduce the functions of several random variables. We cover a function of a single random variable in the third topic itself, whereas after introducing 2 and higher dimensional random variables, we introduce the functions of several random variables. In that we discuss the conditional distributions also. Then in the seventh topic we cover the cross moments, covariance variance matrix and correlation coefficient and so on, that we discuss. Even though we discuss the correlation coefficient and linear regression in detail in the later part, whereas we introduce this via probability concepts. And then the topic 8 we cover the limiting distributions. That means we introduce a sequence of random variable, what will be the convergence or divergence of sequence of random variable and so on. And finally, we cover the central limit theorem in the topic 8. So, with these 8 topics we cover the introduction to probability theory. The word introduction is very important, because we are not going for advanced probability theory, whereas everything is very introductory level in the sense with the simple concepts and some examples and completing the concepts with the simple problems. So, with these 8 topics we cover probability theory, and then the remaining 4 chapters, 4 modules or 4 topics we cover the statistics. So, in these 4 topics we cover statistics, starting with the descriptive statistics and sampling distribution. Even though each one can be a separate topic, but since it is an introduction, we combine descriptive statistics and sampling distribution in one topic, where the sampling distribution can be a separate topic, but here we have combined with the descriptive statistics. Here also we introduce a very simple concepts and some examples. And the topic 10 we cover point and interval estimations. Again, the point estimation can be a separate topic, but since it is an introductory level of statistics course, we combined both point and interval interval estimations in one topic. So, we introduce the concepts of point and interval estimation with some examples and some real world problems also. And in the topic 11 we cover the testing of hypothesis. Here also same thing, the hypothesis testing can be even it can be a separate course itself, but still we have covered it in a very nutshell with concepts and examples. At the end of this topic we cover the ANOVA, that is analysis of variance also. And finally, the topic 12 we cover analysis of correlation and regression. We do not have much material to cover in this particular topic, therefore, we have introduced the definitions and a few examples. The way we discuss topic 9, 10 and 11, relatively we covered less concepts in the 12th one, because the course is meant for probability theory and statistics. Since probability and statistics are closely related with the data analysis and come to the conclusion of probability concepts, and so basically probability concepts are used in the statistical inference, and while solving some of the real world problems using probability, we do the statistical inference from the data side. Therefore, both probability and statistics are well connected in the sense whenever you have a real world problem, whenever you make a probabilistic model, you will use the some data analysis using a statistical inference. And similarly, whenever you study any statistical inference or whenever you have a you have a real world problem that can be solved with the empirical analysis, then you will use some of the probability concepts also there to get the final result and to get the conclusion. Therefore, probability and statistics are linked in a very compact way. Therefore, whenever you study probability or statistics, you can go back and forth, see the related concepts in the other side to understand. And this course is going to be very helpful to in the many of the real world problems whenever you come across and going to solve it. So, I hope you will really enjoy this course, because which is a good combination of probability and statistics. Again, I am saying it is a very introductory level, and whatever the concepts or whatever the problems which need more theory, you can always go to the higher level courses of those concepts. For example, analysis of variance or a non-parametric statistical test, or sampling distribution in detail if you want to study, or logistic regression if you want to study in detail, similarly regression and so on. So, any topic if you want to study in detail, you can always go to the higher level courses and study, whereas here we introduce in a very introductory level. With this, let me complete the introduction about the course, that is Introduction to Probability Theory and Statistics. Let me start with the first module, that is Basics of Probability. In this module, we are going to discuss about the random experiment, then sample space, then axiomatic definition of probability and probability space in the first lecture. And the second lecture, we are going to discuss conditional probability and independent of events. And in the third lecture, we are going to discuss the total probability rule, multiplication rule and Bayes theorem. With that, we are going to complete the first module, that is called Basics of Probability. Let me start with the definition of a random experiment. The first definition, that is called a random experiment. An experiment is said to be random if its result cannot be determined beforehand. Whenever
in any experiment a result cannot be determined beforehand, then we say that experiment is a random experiment. In the whole probability theory, we started with the random experiment. That means we have an experiment in which the results cannot be determined beforehand. We can think of many examples. Over the course, we are going to discuss one by one examples. Therefore, I am going to give the examples a little later. The next definition: sample space. The set omega of all possible results of a random experiment is called a sample space. The sample space is nothing but the collection of all possible results or outcome of a random experiment. That means we have a random experiment in which the results cannot be determined beforehand. If you are able to collect all possible outcomes of a random experiment, that collection or that set of all possible results, that is going to be called it as a sample space. Each possible outcome, that is called a sample. Either possible results or possible outcomes, one and the same. So each possible outcome or each possible result, that is going to be called it as a sample, and the collection of all possible results or all possible outcomes, that is going to be called it as a sample space. Since we have a random experiment of many kind, the set could be consisting of a finite number of elements, or it could be countably infinite number of elements in it, or it could be uncountably many elements. The set omega may consisting of finite elements or countably infinite number of elements or uncountably many elements. Not only that, those elements could be numerals or non-numerals. You may have some random experiment in your mind. All possible outcomes or results of a random experiment, if you make a collection, that collection could be numbers or it could be non-numbers. Similarly, it could be finite or countably infinite or uncountably many elements. So I will go for a few examples for the sample space. Example 1. The easiest example, the random experiment, I use the notation E for random experiment. Random experiment is the, suppose you have a very simplest example, tossing a coin. Tossing a coin, that's a random experiment. The set of all possible outcomes in this random experiment is going to be, I use the notation H for if I get a head. I use the notation H for obtaining head. Similarly, I use the notation capital T for getting a tail. That means the only two possible outcomes are head or tail. So this is the collection of all possible outcomes in this random experiment. Let us go for another example. The random experiment is rolling a dice. Here the all possible outcomes, I show the each side that number, it's a number which I am going to get either the number 1 or I am going to get the number 2 or 3 or 4 or 5 or 6. These are all the possible outcomes. In the dice, whenever you roll, the possible outcomes are going to be either 1 or 2 or 3, 4 or 5 or 6. These are all the possible outcomes. So the omega consisting of all possible outcomes, that all is very important. You should make a set consisting of all possible outcomes. So first one has only 2 elements, whereas the second one has 6 elements. Third example, random experiment is a number of calls, telephone calls ongoing in a particular telephone exchange. Number of ongoing calls ongoing or ongoing calls in a telephone exchange. The omega, all possible outcomes. There is a possibility no calls, or there is a possibility only 1 call, or there is a possibility 2 calls, and so on. Even though it may be a finite number of calls, so I am just putting a dot dot dot, that means it's a huge number. So it could be 1000 or it could be 2000 or whatever be the number. So I am just writing 0, 1, 2, 3 and so on. So many calls are going. This is going to be all possible outcomes of this random experiment. It could be finite also. So this is going to be the collection or set. So you see the first example, it is not numbers, whereas the second example we have numerals, third example we have numerals. So the way you have a random experiment, the collection of all possible outcomes could be numerals or non-numerals, and the collection could be finite number of elements or countably infinite number of elements or uncountably many elements also. Suppose I give a fourth example in which the random experiment is temperature of a particular city. In this random experiment, the omega is going to be, the temperature can vary from some range. For example, it may range from a collection of x such that in that particular city the temperature is most of the times lies between 0 to 50 degree centigrade. Suppose I make the assumption that the temperature is always goes from 0 to 50. So the omega is going to be a collection of values lies between 0 to 50. So it's a real number. Therefore, the elements of omega is uncountably many between the interval 0 to 50 degree centigrade. I have given the example in which it is going to be numerals or non-numerals. Similarly, it could be finite or countably infinite or uncountably many elements also. Now we will move into the next definition, that is called a sigma field, or there is another name called sigma algebra. A collection that is denoted by F of subsets of omega, that is called a sigma field over omega, either you can use over omega or on omega. The omega is a non-empty set, okay, such that the omega is belonging to F. Second one, if A is belonging to F, then A complement that is also belonging to F. A collection F of subsets of omega is called a sigma field over omega or on omega whenever it satisfies these three conditions. The first condition is omega belonging to F. If A belonging to F, then A complement is also belonging to F. The third condition, if A1, A2 and so on that is belonging to F, then the countable union I belonging to 1 to infinity that is also belonging to F. Whether you take a finite elements in the F or countably infinite elements in the F, the union of those elements also belonging to F. If any collection F of subsets of omega satisfying these three conditions, then we call that collection is called a sigma field on omega. So omega has to be a non-empty set, then satisfies these three conditions of collection of the subsets of omega, then it is called a sigma field or sigma algebra. This is going to be a very important to define a probability. Let me give some examples for the sigma field. Then we will go to the definition of probability. Now onwards I won't discuss the random experiment. I will start with the sample space. Suppose the sample space is the same example, head, tail. We can create the sigma field or sigma algebra on omega, that is F, empty set, this is empty set, singleton element, H, tail and omega. You can verify whether all three conditions of the sigma field is satisfied. Empty set is a one element, complement is a whole set, both are belonging to F. The third condition, if I take a few elements, union is also belonging to the same F. Suppose if I take a H as well as a empty set, union is going to be again H, that is also belonging. If I take a tail and the omega, the union is going to be omega, and if I take a head and tail union, then that union is going to be omega, that is also belonging. That is the third condition. Second condition, if I take any one element, the complement is also belonging to the F. So if I take a empty set, complement is omega, that is also belonging, and H complement is tail, that is also belonging to F, and the tail complement is a H, that is also belonging to F, omega complement is empty set, that is also belonging to F. Therefore, all those three conditions are satisfied by this collection, which collection is a subset of omega. Therefore, this is going to be a sigma field or sigma algebra. This is not the only sigma field which satisfies the three conditions. We can have one more sigma field, that is empty set and the whole set. This also satisfies all the three conditions of sigma field, because omega is one of the elements, complement of empty set and the whole set is there, and the union is also belonging to the collection. Therefore, this is also sigma field. So, this is called a trivial sigma field. for any omega, you can always make a sigma field that is consisting of empty set and the whole set. That's a trivial sigma field. Even some books they use the notation that is f suffix naught. If it is f suffix naught, that's a trivial sigma field. So not only this is a trivial sigma field, this is the smallest sigma field also. Since I use the word smallest sigma field, the other one which has a singleton element starting from empty set, a singleton element and the whole set, so this is the largest sigma field. Since it has a 2 elements, omega consisting of 2 elements, if you go for 2 power 2, that is 4. So number of elements in this sigma field F has exactly 4 elements, therefore this is the power set also. This is a power set which is the largest sigma field. In this example, we have a trivial sigma fields. One is the smallest one and other one is the largest one, that's a power set. In between we are not getting any other sigma field. We are getting only 2 sigma fields because it has only 2 elements. One is with the smallest, other one is the largest. Now I am going to discuss some more example. In that we will end up a non-trivial sigma fields other than smallest and the largest. Second example. I won't bother about what is the random experiment, directly I give the sample space. So the sample space consisting of 3 elements. Sample space consisting of 3 elements. Now we will go for creating the sigma field. The smallest one always empty set and the whole set. The another sigma field which I can create, empty set. I take a singleton element A, B and C together. Therefore, A complement is B and C, B and C complement is A, and the union of A, B and C, that becomes the whole set. You can verify. You can verify F1, that is a sigma field because it satisfies all the 3 conditions of the sigma field. I can go for, similarly I can go for another sigma field keeping B separately and A and C together. Similarly I can go for another sigma field keeping C separately, A and B together. That means I can create 2 more sigma field of similar kind. I am going for the largest sigma field satisfying all the 3 conditions, that is empty set, singleton element, any 2 element, AB, BC and CA, and all 3 elements together. Count 1, 2, 3, 4, 5, 6, 7, 8 elements. Number of elements in the sigma field is 3. So 2 power 3 is 8. So this is the largest sigma field, nothing but the power set. So in this example, we have created the trivial sigma fields like the smallest one and the largest one, and in between we have created some more sigma fields. I have created 1. Similarly, you can create 2 more sigma fields. That means for a non-empty set omega, based on the number of elements, you can always able to create many sigma fields, including the trivial sigma fields. And the sigma fields is going to play an important role in the probability that we are going to discuss in the later part. The first example and the second example, we have finite elements, the omega consisting of finite elements. we can go for creating the sigma field when omega is uncountably many elements. Let's go for third example, that is omega is same as the real line. That means the elements is from minus infinity to plus infinity. That is a collection of x such that x lies between minus infinity to infinity. Real numbers, uncountably many. Omega consisting of uncountably many elements in it. Now we are going to create the sigma field on omega. The omega consisting of uncountably many elements. Obviously, here also the trivial sigma field is going to be empty set and the whole set. We can go for a non-trivial sigma field F1 consisting of empty set, open interval minus infinity to 0. The other element is closed interval 0, open interval infinity, then the whole set. You can verify whole set is one of the element, and the second condition is a complement of every element is also belonging to the same collection. Complement of empty set is whole set, complement of minus infinity to 0, that is 0 to infinity, the closed form, and complement of 0 to infinity, that is minus infinity to 0. Complement of whole set is empty set. And if you make a union of any two elements or any three elements or all four elements, that's also belonging to F1. Therefore, F1 is also going to be a sigma field. The way I break minus infinity to infinity at 0, one side open interval, other side 0, you can think of any real number between the interval minus infinity to 0. You can partition the whole interval into two pieces at any real point. Then you can make two elements, then you will have many sigma fields. This is the easiest sigma field one can create by partitioning the interval into three pieces, three subintervals. Then it is going to be little difficult. You have to go for creating a union and the complement of every interval also belonging to F and so on. That is little tedious job, but still you can partition the interval minus infinity to infinity into finite number of subintervals. Then accordingly you put some more elements so that all the three conditions are satisfied. Like that you can create many sigma fields. But we are going to have a largest sigma field. We can just visualize what are all the forms of intervals or elements going to be the element of F or the collection of subsets of omega, so that F is going to be a sigma field, in which it is going to be elements of it start with the empty set, it's with the singleton element A, and it is going to be having the element of A to infinity form. A can be a real number, and it will be of the form A to B. B is also a real number, and it is going to be of the form minus infinity to A, open, and it is going to be of the form closed interval A to infinity, and it is going to be of the form A to B, open interval, both closed interval A, open interval B. Here both A and B can take any real number. So these are all the combinations of different real numbers will land up okay, one more element, that is omega also. So these are all the different forms will form a collection that is going to be the largest sigma field on or over omega, where omega is a real line. Special name for this sigma field, that is called Borel sigma field. This is a Borel sigma field on the real line. Suppose I have a omega which is not the whole real line, it is in the sub interval 0 to 1, closed interval. Then you can always create a f which is a Borel set on real line intersection with the 0 to 1. You don't need to have a whatever the Borel sigma field you created on the real line. Suppose your omega is going to be a sub interval between minus infinity to infinity, then you can always make a sigma field on omega which is a sub interval of a real line by intersecting that interval with the Borel sigma field. Therefore, now we have discussed how to create the sigma field whenever we have omega having a finite number of elements and uncountably many elements. Obviously, when you have a countably infinite number of elements, you can do the similar exercise for creating the sigma field.